Hello everyone. In this session, we are going to study the dynamics of rotational motions. First topic is the rigid body rotations. Second topic is angular momentums. And the third topic is the gyroscopes. First topic is the rigid body rotations. So we consider the rotational motion of a rigid body object. Axis of rotation is expressed with the z-axis. We'd like to consider the motions of the rigid bodies around the z-axis. At first, we'd like to divide the rigid body object into the small pieces. Then, we'd like to consider one of the pieces inside of the rigid body object. So this blue part we are going to consider. And the mass of the blue part is expressed m sub I. This part is m sub I. Motion of equations is expressed f sub I tangent equal m sub I tangent. The tangential component we'd like to consider because we are interested in the rotational motions. So this blue is making the rotational motion around the z-axis with a radius of the r sub I. So acceleration is expressed r sub I times alpha z. Newton's equation of motions is expressed f sub I tangential component. We just write tangent equal m sub I. A sub I tangential component, and the A sub I tangential component is expressed r sub I alpha z. Alpha z is the angular accelerations. Then substitute. Then this becomes m sub I r sub I alpha z. And the alpha z is the same in the all point inside of a rigid body object. And then you can multiply the r sub I in the both sides of the equation. Then r sub I, f sub I, tangential component of the force, m sub I, r sub I square alpha z. Then we'd like to sum up all the pieces inside of the rigid body object. So take a sigma in the both sides of the equations. So I is sum up to the order point inside of the rigid body object. This is m sub I, r sub I squares I. All the elements inside of the rigid body has the same angular acceleration of alpha z. Inside of this part is actually the torque, z component of the torque. This part is a moment of inertia. So finally, we have equations of the rotational motion of the rigid body object is expressed I times sum of the torque equal I times alpha z. This is a basic equations for motions of a rigid body object. Okay, so this is exactly equal to the last equations. So we are going to use these equations, but the left hand side, this part, sum of the torque. So we'd like to simplify the left hand side of the equations. So this is, we are going to consider the internal force. So inside of the rigid bodies, we are going to consider and take two small part of the element. These two elements, force is acting between the two elements. So consider 2 points inside of the rigid body object. The position vectors, this is r sub I. So you can take origins, some point, this point is r sub j. And the internal force means this particle is force is acting on this part is F This is the action and reaction pairs. So magnitude of the force is exactly same and the direction is opposite. So this is the action and the reaction pairs. Then we'd like to calculate the torque. Sum of these two torque. R sub I F. This is internal torque. Plus R sub J. Cross minus F. This is gonna be R sub I minus R sub J cross F. This is a vector product because of the definitions of torque. R sub I cross F, R sub J cross minus F. So you can sum up this is going to be R sub I minus R sub J cross F. R sub I minus R sub J is directed on this line. This is R sub I minus R sub J. R sub I minus R sub J is parallel to the F. Then vector product, it becomes 0. Then sum of the internal torque becomes 0. In the left hand side is the sum of all the torque acting on the every point in the rigid bodies, but all the internal torque, sum of the internal torque add to the 0. Tau sub I z is internal. It's gonna be 0. So you can use this equation. So the sum of the torque, we just only need to consider the external torque when we consider the motion of a rigid body object. Then one more important point is when we consider the motion of the object rolling without slipping. Shape of the rigid body object is a circular shape. This object is rolling on a surface without slipping. Then this point is leaving on the surface. Instead, surface of the rigid body object is going to touch ground. So when the triangle mark is come to the surface, so distance marked by the red curves exactly equal to the distance the ground. These two distances should be the same. Part of the circumference, when the angle is becomes the theta, so this length is expressed r theta. And also the distance expressed r theta. Also central point is moving to the right with the same amount of the distance. This is gonna be r theta. So this is the total amount of the distance for the center is moving to the right. So condition for the rolling without slipping, if you take a small change of the time, is expressed. This distance can be expressed as v sub cm, velocity times the delta t, is the distance for a center to travel, is equal to the r times d theta. This is going to be this length. So by dividing the delta t in the both sides, v sub cm is expressed r times d theta over dt. And the d theta over dt is equal to the omega, angular velocities. So velocity of the center of mass is expressed r omegas. So from this equation, if you take a derivative in the both sides of the equations, it becomes dvcm over dt equal r is constant, so r d omega dt. So left hand side is accelerations of the center of mass a sub cm equal r times angular acceleration alpha. Acceleration of the center of mass is equal to the r times alpha. We are going to use these equations to solve some practice questions. So you got to be familiar with these equations. Okay, this is the end of this session.